So welcome to lecture number 19, and in this lecture we will continue this idea of this machine and operations and all, and then we will begin with a different kind of a structure that we talked last time, which was G cross H to G. So for now we will put it aside and work here. So we have a processor in a machine. A computer has a processor, this operator O, and then we have some data input. These are inputs, right? Inputs in our machine. So these are inputs and this is processor. So a processor takes an input. So here it is taking, these are processor, we have same input, right? These are the same processor, not input, same processor. This processor is coming from this set G. So we have a set G with an operator O. So it is the same processor acting on, so it is coming from, these are coming from G, and these are our data. So these are our data input, and this is coming from H. We can see here these are coming from H, and then there is a operation G going on. This is what we design manually. This is our logic circuit. This is our logic circuit that we can create. Now this operator G acting on H. So it is a processor taking some input. Here is the processing happening. Here is the processing. So this is the processing part. It is processing. And after processing this data, we are getting a different data here. So this is output, right? So this is processing, output, this is input, right? This is this one here. Let me do here. Okay, so this is input, right? And this is our processor. So this is our processor. So now this is true. It means all the output that we have generated through this processing, these all should belongs to our set. It means the output, output cannot escape the logic of computer. It means we have a binary number, the set of binary number, which is 0 and 1. It has only two elements, right? Binary number, the set of binary number, only two elements. Now whatever computation we do on this binary number, this set, let's say I have a binary number B1 and binary number B2, and we do some operation, we get another binary number B3, but this B3 must belongs to our set B. It cannot escape binary number. You cannot expect, for example, add two binary number B1 plus B2 and get an element 2. It is not possible. It is false, 0. Why? Because 2 does not belongs to this set. It is a decimal number, right? So everything in this computer, everything must be closed. It is called closure. So a minimum requirement for any digital machine is it must satisfy closure property, right? Now this kind of machine that only satisfies closure, we call it magma. Now this magma is a stupid machine. We call it a stupid machine because why this machine is stupid? Because it has no capacity. It has no capacity to perform all computing, all kind of computing. It cannot. This machine that only satisfies closure cannot perform all kind of computing. A magma is this machine. A computer that only satisfies closure will escape the set be the binary number 0 and 1 the moment you impose another kind of computation, and the moment it escape this system, it produces error. It becomes error, right? So a computer is designed in such a way that it should satisfy various kind of property, right? And this structure with this definition, right, is a model. You can say it is a model. It is a model of computation. It is a model of computation. Any computing device should follow this structure. Okay? Should follow this structure, because this kind of structure is action. We call it action. It's an action going on. Okay? Now, to make the computer more advanced, more powerful, we have to design a different mode of computation, Well, the different mode of computing device, let's say a machine. So we have the machine, we have some G, a processor, some input data, and some processor here, processing logic here. This logic, right? The star. So what we said, this logic, you're gonna do two things. It's going to take G Cartesian product of this and produces G. Now all mode of computation should follow this structure. You cannot escape this. But it needs more than that. This is just a general architecture of a computing device. A digital computing device, a digital. Right? It could be analog to, doesn't matter, but we are interested in digital machines, right? Now you may be wondering why I'm talking about this, because this is important, okay? This structure is very important for computation. So now what we say that a machine, so what we said, a model, an architecture, an architect of machine, which is computing machine. It is digital. We are interested. So what we're gonna do? We're gonna take this algebraic structure GH and star. So a digital machine has this structure. Now how do we? And what is the star? The star is our logic gate. It is our logic gate. So this star is gonna take G cross H. G is we already talked about this. This is processor. H is our input data, and it is going to produce, this star is going to produce output. Right? Output. Now it already satisfies closure property. And we said this closure property satisfying machine is a weak machine. It is very weak. It is a stupid machine. Now, how do we extend this? Well, we have set binary number 0, 1, right? What kind of a structure we can impose on this? Well, then we have to go to Boolean algebra. I will talk about this a little bit. So what is a Boolean algebra? A Boolean algebra is an algebraic structure. Now, so we have a set B, which is binary number set. Then we have three operations: AND, OR, and NOT. So this is a computing device. The logic behind computing machine. Now this is not enough, because this is still not defined what it is. So we have to define it. So what is AND? Well, AND is B cross B to B. So this is Cartesian product. What is OR? OR is B cross B to B. Now we have to be very careful while defining NOT, because you see, we said binary operation. Well, AND is binary operation, OR is binary operation, but what about NOT? So this is a different kind of algebraic structure. What is AND gonna do? It's going to take element B and it produce another element in B. This is a different definition. NOT is unary operation. It take one element and produce another element, but AND takes two element and produce another element, right? So this structure with this defined, it's called Boolean algebra if it satisfies some axioms. What are those axioms? Well, the axiom will be commutative, closure, associativity, distributivity, complement, and various laws there we have, right? If those laws are satisfied, then we get a full machine, a full digital computing machine, right? So this is powerful machine, right? Now, so this kind of machine has this kind of a structure. Now we said what happens when we not impose this structure and we impose this one, G cross H to G, right? But before that, let me clarify one thing. Why I am talking about this machine and input and process and output, because I think this kind of structure is important, okay? This is important. We have to know these things, right? I'm not only I don't want to talk everything in abstract way, so you have to make things how it is related to other kind of things, right? That is why I gave example of Boolean algebra. But you don't have to, if you do not understand this, then that is perfect. We do not need this, okay? We will talk about this later. So now, what kind of this structure is? Let's talk here. So what do we have here? So we have a set G, some H and some operation H, and this we define G cross H, and this time not to H but G. So what is happening here? So now what kind of structure this is? That is the question. Now we have to see very carefully. Last time we defined this star, a minute ago, like this, G cross H to H. What is happening? This G is set of operator. H is set of, let's say, functions, not functions, I would say, some data, right? These are some data. So what does this structure say? It says set of operator acting on data, and it produces another data, right? So this is D1, this is D2, right? Now this can be this one here. We can say this is like some eigenvalue equations, right? So this structure is this one. What about this structure? What is this saying? It is saying set of operator acting on data produces not data but operator. Let's say some operator, this is operator O1, this is O2, and this is some data. So what is happening here? This is a very different kind of thing going on, right? A very different kind of thing. This structure and this structure is different. So this structure, this O should belongs to G itself, because it is operator, not data. That is why this is H. This is G, because the output should be in G, because output is always operator. But how is this possible? An operator acting on some data should produce data, but it is producing operator. So the thing is, now this operator, this output should not escape G. It means if this operator has to be in the G, then it means this D should be different. The set of H should be something else. Otherwise, this operator acting on some data produces some data, and the data is in H. But we want the output should be in G, but G is set of operator. So this D should be a very different kind of structure. And what is that? Well, then D should be also, this should be also another operator. Think carefully. We have operator O, let's say we have operator A, and this operator, element of G, and let's say we have another operator B, and this is element of H. Now what does star does? It is going to take G cross H to G. It means star is going to take the element of G, which is operator A, element of H, operator H, and cross product, Cartesian product, so we get order pair. And what is this star going to do? Well, it is going to produce G, not G, A star H. A star H. So what is this A star H? It means it is nothing but operator A acting on some operator H. And this is legitimate. It can happen, right? And this, when A operator act on operator H, we get a different kind of operator maybe, right? So this A of H, let's say this is an operator, and we can get another operator C, right? So this AH equal to C. What if here this happens? Let's say what if we switch this? Let's say H acting on A. Let's say we get some operator D. Now is C equal to D, right? That's a legitimate question. So this structure can help us to study the interaction between operator. Interaction between operator, right? Like AH and HA. What is the relation between this, right? This is notation for relation. So if we are checking commutativity, so AH related to HA, we can write H minus HA. For example, this is just an example, equal to zero. Then what happens? Well, then it means, this means AH equal to HA. So it is commutativity, right? So this is commutativity, right? Now what about, but is it always true? Well, it is true when this is 0. What if we define the relation like this? Say AH related to HA by this, AH minus HA equal to some K. Then what happens? Well, then AH is equal to K plus HA. This is not commutativity, right? This is not commutativity. So it is a failure of commutativity.